So let's start with, so we were in the middle of proving some topological results about what figures are. Namely, our goal is a figure is a thing whose boundary has no volume. So in particular, I guess the boundary of a figure is automatically a figure. If something has zero lower volume, it has zero lower volume. But let's talk about the arguments so far. So maybe we'll start with this. If I give you a set X, then what's the interior of X? Other than the intersection of all open sets contained in X. No? Union of all open sets contained in X.
Do you want the ball definition?
Yeah.
Oh.
The set of points in X such that there exists an epsilon greater than 0 such that the ball of radius epsilon centered at P, can't remember the order. Okay, is contained in X.
Yeah, and pictorially this is, if that's supposed to be this set, that point has a little ball around it that's totally contained in the set. So that's an interior point. What does it mean to be in the closure? Well.
Oh, yeah.
But notice this is a subset of X, and I didn't lose anything by doing that. It would be a mistake to do that with closure.
It's an Rn such that we're all epsilon greater than 0. There exists another point in the ball centered at P of size epsilon. Such that Q is not in X.
No.
No.
And let's,
Oh, yeah.
and let's just say that in maybe a shorter way. So if there exists a Q in this and in this, so what's a shorter way of saying that?
Their intersection is not.
Yeah, so you jumped all the way to the end.
Right.
No, it's just, there's a lot of So here is a point that is not in the set X, because I can find a little epsilon neighborhood which doesn't intersect the set at all. There is a point which is not interior, because no matter what epsilon ball I draw, there will be stuff in the epsilon ball not in the set. So there does not exist such an epsilon. But for every epsilon bigger than 0, there does exist stuff in the set. That's stuff in X that's in that epsilon ball. And what was the point? Well, we were going to prove some things classifying the behavior of figures in terms of that. And let's see, the first of those results was that taking the inside of a set doesn't change the inner volume. Taking the closure of a set doesn't change the outer volume, which maybe seems reasonable. X closure is supposed to be everything that has stuff inside of all of these balls, and what does it mean to be an outer rectangle? It means there needs to be stuff in some intersection. Inner volume has an inner rectangle has to do with set containment, and there's something about set containment. But we proved it. And the point out of that was you can compute the outer volume. The volume of the closure is exactly the difference between the outer volume and the inner volume. It's the volume of the boundary. And as a consequence, well, that difference being 0 is exactly what it means to be a figure. So figures are exactly those sets whose boundaries have no volume. So that's what our goal was. And we were in the middle of proving this, and here's how we were going to do it. Maybe I'll summarize the motivation for the first on the board really quick fast. So if we want to show that that's what we need to show. So maybe we'll even try to do better than that. Let's try to show something like, well, let's make some other modifications first. I can replace this set x with the interior of x without losing anything, right? Because v minus of x is the same thing as v minus of the interior. I can also put a closure here. That if I can prove that theorem, then I would just say, well, that bar and circle don't actually matter. So this I'll actually prove in a stronger way. I'll actually try to show that for every subdivision, that equality happens. And, well, you can kind of make sense of what this is. This is the sum over all outer rectangles for the closure minus the sum of all volumes of all inner rectangles. And the claim is that that is the same as the sum of all volumes of outer rectangles for the boundary. Oh, well, but hey, look, this is like add up all the outer rectangles, then subtract all the inner rectangles for the interior. Every inner rectangle for the interior is an outer rectangle. So this is like adding up a subset of that. So you can cancel some terms and see what we really want to show. Yeah. So if you add up all the volumes of outer rectangles that are not inner rectangles for the interior, that's what I'll try to show. And how will I show that? I'll show that that indexing set is the same as that indexing set. So those two sums are just the same sum. And one of the, so that gets us to there. That's why I want to prove that. That makes sense? And we got one of those results already. And let's actually just draw a picture of why that was. So let's suppose you happen to have, here is, let's draw a zoom in picture. Here's one of these j's in delta. Let's say that this j is an outer rectangle for boundary XRL delta. So that means this set, I'll draw it. So there's the set x. The set contains some boundary point in x. So let's see, by looking at this, do you see a point in this set which is not in the interior of x? Well, a point in the boundary isn't in the interior, right? Because the boundary is closure minus interior. So there's a point P in boundary x. That's x bar minus x circle. So that point P is in the closure. So this very rectangle is an outer rectangle for x. But this point is not in the interior of x. So that means this rectangle is not contained in the interior of x. So it's not an inner rectangle. So that's why every outer rectangle for the boundary is an outer rectangle for the closure, but not an inner rectangle for the interior. So that's what we did last time. Let's try to do the opposite. And I think I've given myself space to draw a bit of a picture down there. So let's let J be an outer so if I want to prove a set equality, there are two set containments that need to happen. Let's try to prove the opposite. Let's try to prove that J is, if J is an outer rectangle for the closure and an inner rectangle for the interior, then it's an outer rectangle for the boundary. Let's try to do that. So, let's see. Let's take J to be an outer rectangle and not an inner rectangle. Because J is an outer rectangle, what can we conclude? What's the definition of an outer rectangle for a set?
J intersects X bar is not.
J intersect X bar is not the empty set, so I can find some P in there. So, no, I'm going to draw the picture right here. So, there's the rectangle J. Right here is some, down here, some point P in J intersect the closure of X. As J is not an inner rectangle for the interior of X, that means that J itself is not contained in the interior of X. So there must be something in J that's not in the interior of X. I'll call it Q. So there's some point Q in J with Q not in the interior of X. There. There's Q not in the interior of X. And they're not necessarily the same point. Right? They could be different points. But, I mean, if they were, we would just be like, done, right? So this point Q is already not in the interior. So if that point Q were in the closure, that point Q would be in the boundary. Because the boundary is closure by this interior. So if that point Q were in X bar, we would already be done. That makes sense? So let's think about P also. I already know that P is in the closure of X. That's a bit redundant. So I already have P and J right there. So that point P is already in the closure of X. So if that point P were in the interior, were not interior to X, we would be done. In either of those cases, we would have J intersect boundary of X not equal to the empty set, so that J would be an outer rectangle for the boundary of X, well, delta, and that's exactly what we want. We want to show that if J is in that set, then it's in that set. But I claim that it's possible that neither of those happen. In fact, let's draw a picture. Let's suppose that Q is not interior. Nope. Assume that Q is not in the closure, and let's assume that P is in the interior. So let's see what that means. If that P is in the interior, that means there must be like a little ball surrounding P that contains only stuff in X. So there must be a little ball right here. That whole ball is contained in X. This Q right now is not in the closure. So there must be some little ball surrounding Q which is totally disjoint from X. And I mean, I guess generically, what does this mean? That means that, like, the picture should look something like that. P is a point that's interior to X. There's another point in this same rectangle that's not even in the closure of X. And this picture is, I mean, dishonest because I've drawn it like there's this boundary curve. I don't know that such a thing should exist. But following this picture, how would you want to construct a point that is in the boundary?
intermediate value.
Yeah, there's like something intermediate value going on. I mean, there's not like, it's not like this is measuring naturally to a number, or that's going to a number, which is fine. But let's try to do something intermediate value-y. So here's like a straight line from P to Q. Does it look like there's a point where that blue curve has a boundary point for the green thing? Yeah, like this point ought to be a boundary point. So it looks like, I don't know, the last point in the line, which is in the closure of X, should be a boundary point. That seems reasonable? All right, that motivates the following assignments. Let's set L of t to be the parameterization of the straight line from P to Q. Have I actually done that correctly? When you plug in t equals 0, do you get P?
Yes.
When you plug in t equals 1, do you get Q?
Yes.
Awesome. I guess the parentheses around the t are unnecessary and silly. Oh well. I will now, so since I want like the last thing in L of t, which is in X closure, well, that sounds an awful lot like I want to take some sort of supremum. Right, last is like biggest. Not every set has a biggest thing, but bounded sets have a supremum. So let's take S to be all of the t values for which L of t is in the closure of X. So let's, the point which it looks like we want is like the supremum of that set. I want to take the supremum of that set and then send it forward by L. That will give us that little dot. That makes sense as far as motivation goes? It's not a proof because this picture indicates the set X is much nicer than it needs to be. Let's try to study this. So what types of sets have supremum? Have a supremum?
Bounded.
And one other condition. Not empty. Let's show it's not empty. By looking at this picture, can you think of a t value for which L of t is in X closure?
I suppose 0.
0 seems reasonable, because 0 is supposed to go to P. And we have assumed, in fact, P is in the interior of X, but it's also in the closure. Every interior point is in the closure. So by assumption, L of 0 is equal to P is in the closure of X. So 0 is in S by the very definition. So the set S is not empty. The other condition we need is the set S has to be bounded above. Can you think of an upper bound on this set S?
Q.
Q is not a real number.
1.
There you go. So S is certainly contained in 0, 1. So 1 is an upper bound. Cool. So, I mean, you know what comes next. Let's let S be the supremum of this set big S. And in that case, it sure looks like that point right there is L of S. And I'll draw my little s as a cos of S to make sure that it's really different from big S. You don't have to if you don't want to. All right, well, I guess first we should actually convince ourselves that L of S is in the rectangle. If you take 2 points inside of a rectangle, is the straight line between those 2 points contained in that rectangle?
Yeah.
Yeah, and you could check that coordinate-wise. Yeah, there's the assertion that that works. I claim that this point L of S is definitely not in the interior of X. Because that's one of the things we need, right? To be a boundary point, you need to not be interior, but you do need to be a closure point. So I need to, well, I've erased the things. So if at one interior point you would have that there exists an epsilon bigger than 0 such that the ball centered at L of S of radius epsilon is contained in S. So I need to show that for every epsilon bigger than 0, that same thing happens. For every epsilon bigger than 0, this containment is false. That's what I need to show. Let's try to do that. So let's consider any epsilon bigger than 0. The parameterization of the straight line is probably a continuous function, right? It is. So since it is continuous, it follows that there exists a delta bigger than 0. I suppose that delta would even be like the norm of p minus q or something. 1 over the norm of p, epsilon over the norm of p minus q, I think. There exists some epsilon bigger than 0 such that for every t in 0, 1, if absolute value of s minus t is less than delta, then absolute value of L of s minus L of t is less than epsilon over 2. And I won't tell you why I'm going to use epsilon over 2, but it'll come out in the wash. That's a reasonable enough thing to take anyway. Epsilon over 2 is positive. Let's see. So is S plus delta over 2 in the set big S? What is little s by definition? It's the supremum of big S. So could S plus delta over 2 possibly be in the set big S? No, because it's bigger than. Oh, nice. But that means that we can conclude not the definition of the set big S holds for S plus delta over 2. And if you remember, well, there it is. It's all things in 0, 1 for which L of t is in the closure. So it must be L of s plus delta over 2 is not in the closure of x. Everyone feel pretty okay? Oh wait, but if it's not in the closure of x, could it possibly be in the set x? No. X is a subset of the closure of x. So it follows then that f of L of t plus delta over 2 is not in the set big S. Oh, but wait, by our trace of delta, the absolute value of L of s and L of s minus delta over 2 is less than epsilon over 2, which in turn is less than epsilon. Oh, hey. From that, so from that follows that this point is in, all the little f's should be little l's. This point must be in the ball, centered at L of s of a radius epsilon. But we also have that this very point is not in the set X. So it must be that this ball is not contained in S, and so f of s is not interior to it. Does that make sense? Okay, let's talk through it. So let's just, I'm going to write just on the board what the individual conclusions are. There was the false conclusion we wrote down. The second conclusion was that the difference between L of s and L of s plus delta over 2 is less than epsilon. So let's just try to put these two things together. So that means that this number, L of S plus delta over 2, is in the ball centered at L of S of radius epsilon, but is not in X. So if there's a point in here that's not in there, this is not a subset of that. Picture-wise, there's that point L of S. There's the point L of S plus delta over 2. I know that this point is not in X, so there's explicitly something in here that's not in that ball that's not in X. That's exactly what it means to not be a subset. So, whew. So, let's keep track of that quantifier. Did this work for absolutely every epsilon bigger than 0? Did I start by considering any epsilon bigger than 0 before I came up with the delta and did all this other stuff? I think so. Yes.
Says in particular, should that T be into S?
Yeah.
Okay.
Yes, I apologize for that. That's why you were upset.
Okay, then.
Yeah, L of T plus delta over 2 wouldn't really be meaningful. T isn't a sign.
That's the confusion.
Okay, so I was explaining the easy stuff and you were confused about the long stuff. Nice. So that gives us one of the two things. This point is not interior to X. We still need to show that it is a limit point, a closure point. So now I need to show that f of s is in X bar. I'll keep hold of the same choice of epsilon. So epsilon is universally quantified. That delta depends on epsilon. And I'll use those same values. S is the supremum, so it's the least upper bound. So S minus delta over 2 might not be in the set big S itself, but it's not an upper bound on the set big S. So what does that mean? There exists some T in S with, well, that's what I'll actually use, but what do you actually get? You get S minus delta less than T less than or equal to S. Oh, and all those S's should be little s's. Right, that's what you actually get out of the definition of supremum. From that, does this in absolute value inequality follow? Good. Okay, but this function L, also known as f apparently, is continuous. So that means that L of t minus L of s is less than epsilon over 2. So, oh wait, does that mean that this point L of t is in the ball of radius epsilon centered at L of s? It does. In fact, it's inside of the thing of radius epsilon over 2. But that's also not quite what we need. Since t is in S, I can conclude that L of t isn't necessarily in X, but it is in the closure of X. But wait, this is the type of game we've played before in like Calc 1 at some point. So this will seem maybe a little bit familiar. Let's draw a picture. So. I've just found there must be a point in the closure of X within that epsilon neighborhood of L of S, within that epsilon over 2 neighborhood of L of S, in fact. But wait, if that point is in the closure of X, does that mean there has to be stuff inside of X really, really close to that yellow point? That's the definition of closure. So L of t is in the closure of x. So there must be some x in actual x with absolute value of x minus L of t less than epsilon over 2. So I can find some other point. So that length is less than epsilon over 2. That length is less than epsilon over 2. So it's the longest that the other leg of that triangle could be. By the triangle inequality epsilon. Cool. So the distance from L of s to x is less than or equal to the distance from L of s to L of t plus the distance from L of t to x. And you add those two things together, that's less than epsilon over 2 plus epsilon over 2, which is epsilon. Oh, hey, does that mean we found a point inside of the ball centered at L of s of radius epsilon, which is also in the set big X? So that intersection is not empty for absolutely every choice of epsilon. So L of s is in x bar. And now you know what's going to happen next. L of s is in x bar. L of s is in the interior. So L of s is not in the interior. So L of s is in the boundary of x. Well, wait, that means we just found a point inside of this rectangle J, which is also a point in the boundary of x. So that means that this rectangle intersects the boundary, has non-empty intersection with the boundary of x. So it's an Odo rectangle for the boundary of x, which is exactly what we wanted to show. How does that feel? Does that seem okay? There were a lot of moving parts inside of that little subclaim. But now, well, let's just finish it. So that completes the proof of this claim that the set of outer rectangles for the boundary of x is the same as the set of outer rectangles for x minus the set of inner rectangles for x. I assert from that it should be clear that v plus of x delta minus v minus of the interior of x rel delta is equal to v plus of boundary x rel delta. Do you guys actually believe that that's clear? You want me to talk through why? You want me to write more stuff? Okay, I write more stuff. So let's do it. Let's just write down some relevant sums. Yeah, there's actually plenty of space here. So let's write down v plus of x bar rel triangle minus v minus of x soc rel triangle. Let's just write down what that is. So that's like two different sums, right? What's the definition of v plus?
The sum of all the volumes in the powder of X bar.
Yeah. It's the sum of volume of J, where J is in out of x bar delta. And then I need to subtract off the inner volume. What's the definition of inner volume of x rel delta?
The sum of the volumes of J is where J is in of X. So
Good. So those sums have some terms in common, right? If J happens to be an inner rectangle for the interior, then it's also an outer rectangle for the closure automatically. Our point point in the closure has to be a point in X. A point in X is a point in the closure. So every one of these is one of those. So I can subtract those by just taking all of these terms, but then not counting those terms. So that should be the same as the sum. I'm going to make this summation symbol like really fat, because there's going to be a lot in the subscript. J in out of x rel delta, but I'm not going to use any of the j's in x bar rel delta, in of x soc rel delta. Fair enough. Okay, but what did I just show that out of x bar rel delta minus in of x soc rel delta is? Hey, is that an outer volume? It's the outer volume of the boundary x rel delta. So that justifies that little green claim. Cool, so let's just finish this up. So I can always find subdivisions which do a good job approximating the inner and outer volume. And in fact, by taking like a common refinement, I can get a single subdivision that does as good a job as I need on any collection of figures, any collection of sets. So that means I can arrange that v plus of x minus v plus of x rel delta, x bar rel delta, is less than any epsilon I want. I can get this to be less than any epsilon I want. I can get this to be less than any epsilon I want. Maybe since none of those inequalities are the one that I actually need, you can tell that I'm going to divide by this epsilon by something. I guess there are 3 of them, so maybe a good guess would be divide by 3. But we won't yet. So by the triangle inequality now, so LaTeX sometimes does an interesting thing with spacing. When there's like something really big on the next page, it'll space this all out. So it's convenient there was that space, but it wasn't intentional. So let's use the triangle inequality to get something. Let's try to compute that. And you know the game with the triangle inequality. We'll like add and subtract things that are close to each term. What's something that you know that's close to being equal to v plus of the closure of x by the previous page?
V plus x bar delta.
And I'll just remember later on that I need to add that back. Minus v minus of x soc delta. What's something I know that's pretty close to v minus of x? I didn't write delta there. What's something that's really close to v minus of x soc? Yeah, the thing with the delta put back.
Yeah.
And there's also something that's really close to the upper volume of the boundary of x, namely v plus of boundary x rel delta. Oh, that was supposed to be green. All the things in green I still need to uncount in order to preserve equality, right? So I now need to add v plus of x bar rel delta. I need to subtract v minus of x soc L delta. And I thought I gave myself enough space. Minus v plus of boundary x L delta. And now let's just look at the terms. So let's look at the three green terms in the back. Oh, and there should be a closed absolute value bar at the end of this. So those three last terms, what do they add up to be? Zero. Nice. That's good. That's less than epsilon. The difference between those top two terms, what about that? How big is that?
Less than epsilon, and we're going to divide it by 3, so.
Less than epsilon, presumably divide by 3. So now you already know what I'm going to write. So the next step, I'm just going to write down what the triangle inequality gives me together with a 0. And then I'll use this bound that things are less than epsilon over 3. And then 3 times epsilon over 3 is epsilon. So, like, you know the game from here. I suppose I should keep writing for the sake of completeness of my own copy of the notes. So this will be less than or equal to v plus of x bar minus v plus of x bar L delta, close absolute value bar, plus absolute value v minus of x soc minus v minus of x soc L delta, plus absolute value v plus boundary x minus v plus boundary x L delta. And it looks like I'm in a really bad place for space, but as you pointed out, the remaining terms add up to 0. And each of those pieces that aren't 0 is less than epsilon over 3. You add them up, you get something that's less than epsilon. I guess I should go back to the previous page and divide my epsilon by 3. Right now I have 3 times epsilon. Epsilon over 3, epsilon over 3, epsilon over 3. Oh, wait, so there was a whole, like, my actual theorem didn't involve closures or interiors, right? But what is v plus of the closure of x equal to? Just v plus of x. V minus of x plus v plus, well, this is just the boundary of x, that's just how it is. That's less than epsilon, and that's true for every epsilon bigger than 0. Oh yeah, there are absolute value bars around things too. So that's less than epsilon for every epsilon bigger than 0. Oh, that changed the sign, that's silly. So that means that absolute value actually has to be 0. So v plus of x minus v minus of x is the same thing as the volume, outer volume of the boundary of x, which is exactly what we needed. And maybe that's even a good illustration of the power of passing to the interior and the closure. It was much easier to compare the interior and the closure, the volume of those subdivisions, the L delta stuff, because we got an equality on the nose. Otherwise, we wouldn't have gotten that. There are rectangles that are outer rectangles for x and not inner rectangles for x, and yet are not necessarily rectangles, outer rectangles for the boundaries. So let's, I mean, with 5 minutes and no point in me giving you new notes, let's just prove this corollary. So let's let x be bounded. That x in the figure I claim is true if and only if the outer volume of the boundary is equal to 0. And I mean, I think you guys can copy through this. Why should that corollary be true?
Outer volume of x should equal the inner volume of x if it's integral.
Mm-hmm. Or if it's a figure.
Yeah.
So f is a figure if and only if v plus of x equals v minus of x. So that's just the definition of a figure, and that's an if and only if, right? make it silly to say that a statement in a definition isn't infinite. It's the definition. All right. What does that have to do with the statement that v plus a boundary x is 0? The theorem we just proved, what does it say? And is that equivalent to these two things being equal? Yeah, it's not equal. So maybe I'll put something in green. Or equivalently, v plus of x minus v minus of x equals 0. Because that is the same, right? Two things are equal if and only if their difference is 0. By theorem 6, that's equivalent to v plus of boundary x equals 0. So, what are figures? Figures are sets whose boundaries aren't necessarily empty, or contained in them, or subsets of them are anything. They're sets whose boundaries have no volume. Cool. And, I mean, I've gone over at least 3 times by a minute, so I think I can give you 3 minutes back. Ooh, though maybe